Hello. This flipped classroom is about the lipids, which is the last biomolecules that we are going to talk about in this chapter. The lipid is a kind of special biomolecules because there are kind of mix of the things that cannot dissolve into water, and if there is not belong to the categories of carbohydrates or nucleic acid or proteins and indissolved into water, then they are called lipids. So lipids can be summarized into maybe 8 major categories here. As you can see, there are several different kind of things included into the family of the lipid. Now I want you to go through from the very simple structure to the very complex one. But anyway, from this lipids family, we can divide them into 2 major types. First of all, 1 to 6 is a kind of derivatives of fatty acids. And then 7 and 8, there is nothing about the fatty acids. So the majority of the lipid family is belong to the fatty acid derivatives. So you have to know or understand the structure of the fatty acid first. So what is a fatty acid? Fatty acid is normally kind of carboxylic acid with a long chain hydrocarbon. And with long chain hydrocarbon, even though we have hydrogen bonding of carboxylic acid part here with the water, but this kind of thing cannot be dissolved into water because of the very long London force or hydrophobic interaction over here. And the fatty acid is a kind of core structure of these kind of lipids. Okay, so first of all, the fatty acids can then condensed because of the functionalities here, the carboxylic acid, as you know. Carboxylic acid is very reactive and they can react with bases like sodium hydroxide, ammonia, things like that. And also it can condense with some nucleophile. For example, starting from fatty acid, it can condense with some other things. So waxes. What is waxes? Waxes are a family of lipids that belong to the derivatives of fatty acids condensed with fatty alcohol. So if you know the fatty acid, so fatty alcohol is very simple, right? Because if fatty acid is the carboxylic acid with long chain hydrocarbon, then fatty alcohol is the alcohol with long chain hydrocarbon as well. So long chain hydrocarbon of alcohol condensed with the long chain hydrocarbon of the fatty acids. As a result, you will get this kind of compound. Okay. So black part is the alcoholic functionalities, and the pink part is carboxylic acid. They condense together with the ester bond labeled in green color over here. So these are waxes. Normally, our group of the waxes can be varied from a short one to a very long one, like 30 or 30 plus carbon number in the chain. So these are waxes. And then from waxes, fatty acid can condense with other things as well. This is fatty alcohol, right? So we have very long chain alcohol here. But for triglyceride or fats and oil, you have another kind of alcohol. And this kind of alcohol, I can draw it like this. May I put it over here? So this is a kind of alcohol, but triol actually. We call these as glycerol. Glycerol is a trihydroxy compound composed of 3 carbon atoms, 3 OH groups in each particular carbon atoms like this. And then, so because we have 3 functionalities of hydroxy group, they can then condense with 3 carboxylic molecules. So the triglyceride over here, the structure is something like this. Let I draw it like this. Sorry. I should draw it like this, actually. Okay. This is glycerol. Okay, then after that, your glycerol molecule condensed with carboxylic acid. So I put the carboxylic acid, the first carboxylic acid chain over here. And we have 2 hydroxy group left here, right? So they can also condense with 2 other carboxylic molecules. And you have this. So this is called triglycerides. You may heard about this name, triglyceride, since your high school or your primary school maybe. The triglyceride can be divided into fat and oil. Depends on the physical properties. So if the mixture here, normally this kind of thing is a mixture of compounds, because in your biological system, in your cells, there are several types of fatty acids. Depends on the number of carbon inside. So the triglyceride is kind of mixture of several fatty acids condensed with glycerols. If that kind of mixture appeared as liquid phase, we call them as oil. And to be precise, because you may confuse with the petroleum oil, so we call this kind of thing as fatty oils. And if it appears as fat, as solid, we call this triglyceride as fat. Okay, so it depends on the state of the compound. Then from triglyceride over here, as you can see, the glycerol condensed with 3 carboxylic acid. Now, if the glycerol over here condensed with something else, okay, we have 3OH carboxylic. I would move it toward the right hand a bit. Okay, so from glycerol, okay, first oxygen, second oxygen over here, I would push the last oxygen on the bottom here to the left hand. Okay, I will have this kind of thing. Okay, so first OH condensed with carboxylic acid. You have long chain hydrocarbon over here on the right, second carbon like this. And the last one, instead of condensed with carboxylic acid, I will condense your glycerol with some other kind of acid. This thing is similar to the reactions of the structure of nucleic acid. From nucleic acid, you know that the ribose sugar condensed with nuclear base or nitrogenous base, and then another arm of OH group can then condense with the phosphoric acid. This as well can condense with the phosphoric acid, so making the phosphate group like this. So phosphoric acid condensed and then producing the phosphate ester bond over here. So we have triester as well, but the first 2 ester bonds condensed with the carboxylic acid, and the last ester bond is the condensation between phosphoric acid and the glycerol or the alcohol here. Okay, so this is called phospholipid because it is the lipid which has the phosphate or phosphorus in the structure. So we call this as phospholipid. Now next, the sphingolipid. Sphingolipid is something similar to the phospholipid, but we changed something. As you can see from the name, phospholipid is the name of the phospholipid, meaning that there is a lipid that has the phosphate group in the structure. So sphingolipid is the lipid with something called sphingo something, right? Actually, it's sphingosine. Now let's look at the structure of the sphingosine. So sphingosine composed of this. The sphingolipid is composed of the sphingosine. The structure of sphingosine is like this. It is a 18 carbons compound, very long. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, we have 18 carbon atoms included in this kind of long chain structure, and it's quite similar to the glycerol actually, because the glycerol composed of 3 carbon with 3 OH, right? But now 3 carbon here instead of 3 OH. In the middle we substituted the OH group with the amino group, and then we have a long chain with double bond over here. So this compound is called sphingosine. Sphingosine, S-P-H-I-N-G-O-S-I-N-E. This is the sphingosine. So because we have the long chain hydrocarbon over here, 3 functionalities over here, this functional group is very reactive. So it can be condensed with carboxylic acid, making the amide bond. So instead of ester bond as others, this one will create the amide bond instead. So I will label the amide bond with the green color again. And then this one would be condensed with the fatty acid. Okay. So fatty acid is normally a very long chain over here, right? So the structure, as I said, is quite similar to this one because you have 2 of long chain hydrocarbon things dragged to the right hand side. Okay. Now from sphingosine, we have this condensation, but this is not the phospholipid yet. This is called ceramide. From ceramide, the OH on the left hand can then condense with the phosphate group or phosphoric acid. So at the end, you have this. And this is called sphingolipid. So as I said, sphingolipid and phospholipid are quite similar because you have the very polar group of the phosphate on the left hand, and then you have 2 tails of hydrocarbon chain dragged to the right hand. Okay, so these is the phospholipid and sphingolipid. So they are quite commonly found on the cell membranes. Okay, with the very similar structure style. So we'll talk about why this is the suitable to making a cell membrane and things afterward. Okay, we come to the last type of the fatty acids derivatives, which is called the prostaglandins. Prostaglandins is, because of the confusion, this kind of thing is firstly found in the prostate gland. So we call this as prostaglandins. But actually, the prostaglandins can be found in any other places around our body as well. Okay, so what is the prostaglandins? The prostaglandins is a kind of compound that derived from carboxylic acid as well, but derived from the very special carboxylic acid, which is called arachidonic acid. So now take a look at the structure of arachidonic acid, because arachidonic acid, is the acid that is the kind of starting materials for making prostaglandins. It's a 20 carbon chain. Okay, 1, 2, 3, 4, 5. Carbon number 5 make a double bond. Okay, this is polyunsaturated fatty acid that I will talk about it later. That means we have fatty acid with several double bonds in the chain, and the double one is like this. So we have 4 double bonds over here, and with a total number of 20 carbon. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. This is the arachidonic acid. So from arachidonic acid, the prostaglandins is a kind of derivative of this arachidonic acid by chemical reaction, actually. Using enzyme, this arachidonic acid will change the structure to be something else. Normally, arachidonic acid is transformed by some of the enzyme. The majority of this type prostaglandins compounds are composed of C20 like this with kind of 5-membered ring, which was condensed from some places around here. So roughly, the prostaglandins adopt the structure like this. So the common structure of prostaglandins normally composed of 5-membered ring over here by condensation of some carbon around here, and then the rest of the carbon is like expanded into the right hand. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, things like that. So normally they are condensed down here, and some of the double bond was already transformed, but some of the double bond may remains in the structure like this. And sometimes your arachidonic was also oxidized or functionalized with some other chemical functionalities like OH group, or maybe even the peroxide, thing like that. So this is the kind of prostaglandin structure. There are several hundreds of prostaglandins found in the nature. But yeah, as I said, the common structure is actually derived from arachidonic acid with some biological metabolism system. And the common thing is we have like 5-membered ring over here. Okay? So it's a kind of mixture of compounds with the structure like this. So we call this kind of thing as prostaglandins. Okay? Now, these all the things are derived from carboxylic acid, as you can see from the fatty acid. So we will start from describe what about the fatty acid over here. But before that, we have two things left here, right? So let I go through the rest of the family, the terpenoids and steroid and the polyketide. Now, the next type of lipid is terpenoid and steroid. So what is terpenoid, what is steroid? The building block for terpenoid is this molecule. You may have seen this kind of thing in the polymer, right? Because the natural rubber or para rubber is using this one as a monomer and then condensed, forming kind of polymerization process, forming a rubber or para rubber. So the name is isoprene. Isoprene. This isoprene is actually in our body because this cannot dissolve well in water, right? So in our body, it may appear as this derivatives instead. It's a kind of phosphate of the isoprene. So as you can see from the structure over here, you still have double bond on the left hand, but double bond on the right hand was added with the phosphoric acid, so you have this kind of thing. So starting from these molecules, they condense together. Several isoprenes unit can condense together, forming bigger molecules. There are many examples of terpenoids. Right? The condensation between isoprenes units called, the product is called terpenoids. For example, this one. So if I have like two of the isoprene over here, and then they condensed up together. So as a result, we have this kind of molecule. By some kind of chemical reaction, we have this kind of molecule. And this is the limonene. Limonene is the alkene of lemon, so we call this as limonene. Limonene is a scent or fragrance of the lemon. So from lemon, if you squeeze it and you can smell it, right? This compound specifically is the limonene. Some of the isoprenes can also not only condensation like this, it can be further functionalized with some other functionalities. For example, this one. This one. This is alcohol, so it's ended the names with O. And this is found in mint, so this is called menthol. Menthol. Okay. So this is also the terpene or terpenoids compound. So terpenoids is something like this. Using the isoprene and condense them together, several isoprene units, condense them together. So we have this kind of small molecules, and not only just two isoprene units, sometimes the terpenoids can be very, very huge molecules. So I will give you these examples. It's quite large, it's quite huge. So I have this. Okay. very huge one. Okay, as you can see, we have very long pi conjugated system from this ring to that ring. The number of carbon is about 1, 2, 3, 4, 5. This is actually the first isoprene unit, if you can notice. This is the first isoprene unit. This is the second isoprene unit, and this is from the third isoprene unit. This is the fourth isoprene unit. So in total, we have 8 isoprene units. Each isoprene unit contains 5 carbon atoms. So 5 multiplied with 8. In total, we have 40 carbon atoms. This is totally non-polar, and this is called carotene or beta carotene. So as you may notice by the name, it is the alkene from the carrot. And yeah, this one is also produced by condensation of the isoprene unit. Several isoprene units altogether, 8 isoprene units to be exact altogether. And after you digest the beta carotene, you produce this kind of thing. So beta carotene, after digestion, right? Normally our body will cut down the beta carotene in half, okay? And by oxidation as well, we have aldehyde as a product. And this is the name of this is retinal. Oops, sorry. Retinal, because it's the aldehyde of retina, so we call it retinal. It's found in our retina. So we use this kind of compound for detect the light or detect the photon, right? So this is called retinal. So retinal or vitamin A is kind of metabolized from digestion of the beta carotene, and yeah, it's composed of 4 isoprene units. Okay, so terpenoids thing is something like this. It's starting from isoprene and then just condense up together to have a kind of very non-polar molecules, long chain, or maybe very small molecules like this, composed of just 10 carbon atoms. Okay, these are the terpenoids. But what about the steroid? Steroid is kind of condensation of the isoprene units altogether as well. But the style of condensation is different from terpenoids. Terpenoids is, yeah, as you can see, there are kind of several fancy structures derived from the isoprene unit. But if the pattern of the complexation of the condensation give you the 3 or 5 or 6 membered ring and 1 or 5 membered ring like this, any kind of compound containing this kind of core structure, we call this kind of thing as steroids. And actually the steroids here is come from the condensation of the isoprenes. But the patterns of condensation give you this kind of structure, 3 of the 6 membered ring and 1 of the 5 membered ring. For example, the cholesterol is a kind of steroid as well. So what is the cholesterol? Cholesterol is this one. With a double bond. Here, sorry. With this, the double bond at this position. So this is cholesterol. So cholesterol is a steroid as well. But there are several other types of steroid. You may heard about the name steroid hormones, right? So steroid hormones like testosterone is the steroid hormone as well. That testosterone adopt the structure, something very similar to this, composed of 3 of hexagon and 1 of the pentagon, condensed together in this kind of zigzag style. So these are steroids. Okay, so steroids can act as a hormones, right, to be used in our body. Last type of the lipid is called polyketide. So what is the polyketide? Polyketide is starting from a kind of compound that you may be familiar with the name, is the coenzyme A. Okay. Coenzyme A is a huge molecule derived from adenosine, and then with the long chain. At the very end, we have SH group or thiol group. The thiol group then condense with the acetyl group or acetic acid to give you this kind of thiol ester. Okay, so this is called acetyl coenzyme A. Acetyl coenzyme A. A stands for a adenine or adenosine here. So from acetyl coenzyme A, we use kind of common organic reactions that you may not heard about it yet, but next year you will learn about this kind of reaction in organic chemistry. We use kind of aldehyde condensation is the name of reaction, aldehyde condensation, and condense all the acetyl group together. So starting from acetyl coenzyme A, we ended up by condense all these things together. So as a result, you have this kind of compound composed of several ketone units. As you can see, by condensation, we have ketone, okay, and so on. Okay, this kind of structure. So we call this as polyketide. Okay, so what is polyketide using for? Polyketide can be derived to be something else. Like starting from polyketide over here, our body just reduce or cut out the double bond O and change it to be CH bond. So from this one, you end up with this instead. For example, if the last unit here is still attached to the coenzyme A, SH CoA here, right? So you have the ended unit would be S-CoA. Yeah. So this coenzyme A is now, instead of attaching with the acetyl group, it's attached with some kind which is very similar to fatty acid, right? So from this one, by hydrolysis of this, you will end it with carboxylic acid. So this is how our body can, one of the way that our body can synthesize the fatty acid out of acetyl coenzyme A using the polyketide structure over here. And also polyketide can condense in some other style as well, making normally our body or in the cells, when they want to make kind of aromatic ring, they use polyketide as well. So if you look at kind of this one, which, okay, and then they just condense around here, so making double bond over here. So at the end you have kind of cyclic structure, hexagonal structure, thing like that. So with biosynthesis, very complex reactions, they can form kind of fused ring aromatic system from this acetyl coenzyme A, from this polyketide. One of the compound that I want to show is like this one. You may be familiar with the name, the aflatoxin. Aflatoxin is a kind of aromatic compound composed of several functionalities, but originally it is the polyketide. Okay, this is aflatoxin. Aflatoxin, which is a toxin, a kind of toxin produced by kind of fungi that is found commonly in kind of beans, thing like that. And it is very toxic, called aflatoxin. As you can see, where we have aromatic ring, we have kind of, so the structure is changed from polyketides over here to be something very complex. And you may not notice that there's once being thing like this. Okay, but that's fine. It's quite complicated, and you may learn about this one when you reach the biochemistry courses, thing like that. Okay, so as you can see now, we have several types of lipids thing, but in this general chemistry, I will focus into some of the structure. Like I will go from fatty acid first to introduce you to the structure of fatty acids, the common structure of fatty acids, which is very important because the physical properties of the fatty acid will reflect us in other derivatives of fatty acids as well. So after fatty acids, I will go to the diglycerides, which is very important, and then to phospholipid and sphingolipid. So we focus on just 4 of this type. Let's begin with the fatty acid first. Now if you look at the fatty acid, this is a very important thing because it's the building block for the rest one. So fatty acid, you have to understand the structure and properties of this one first to describe the structure and properties of the rest. So fatty acid can be divided into 1, saturated fatty acid, 2, unsaturated. As you can see earlier that I've talked about the polyketide. Fatty acid is constructed from the polyketide by condensation of acetyl group. So each acetyl group contains 2 carbon atoms. That means the total number of carbon atoms in fatty acids, normally they are in even number, like 16 carbon, 12 carbon, 14 carbon, or 20 carbon, things like that. Okay, so because it's condensed from acetyl coenzyme A or acetyl group with 2 carbon atoms. So anyway, saturated fatty acid is a fatty acid, okay, with long chain hydrocarbon like this, 1, 2, 3. For example, this is 16 atom, or maybe you can go to 18 atoms like this. So the name is changed by the length. For example, 16 carbon atom saturated fatty acid is called palmitic acid. And 18 carbon atoms like this is called stearic acid. There are several names, but you don't have to remember all of that. Anyway, there are unsaturated fatty acids as well. And unsaturated fatty acid can be divided into 2 major types. Monounsaturation and polyunsaturation. For monounsaturation or monounsaturation, normally it is like this, starting from fatty acid, saturated fatty acid. So in the cells, they have some kind of enzymes that can dehydrogenation or take out 2 hydrogen atoms from the chain. And by this kind of thing, it puts the double bond into the structure. So this is monounsaturation. You have only 1 double bond in the structure. Normally, it almost always appeared at carbon number 9 and carbon number 10. And the isomer of the double bond is majority in natural abundance of the double bond here is the cis isomer. Like this. So cis isomer means that the double bond is curved to the same side. Trans isomer with the chain of the hydrocarbon is elongated along the double bond. So the double bond group from the double bond point out to the opposite direction, but this is point down to the same direction. So make it curve down like this. Okay. So this is cis isomer, and this is trans isomer. The natural abundant unsaturated unsaturated fatty acid is this cis isomer at carbon number 9 and carbon number 10. This is controlled by the enzymes and mechanisms. So you don't have to really understand what happened in the enzyme to make it cis isomer at carbon number 9 and carbon number 10. Anyway, this is monounsaturation. We also have the polyunsaturation. For example, this one. So 18 amino acid to 12. For example, this one. This is 18 amino acid, 18 carbon in fatty acid, and we have dry unsaturation. Right? We have 3 of the double bonds. So for polyunsaturation, sometimes we have 2 double bond, 3 double bond, or many more. It depends. Okay, this is polyunsaturation. And if you look at the number of look at the position of the double bond. So normally one of the double bond present in carbon number 9 and carbon number 10. And for this, it's still at carbon number 9 and carbon number 10. And if you look at the last double bond over here, the last double bond is on the carbon number 3, but counting from the end of the line here. So we call this position as the omega 3. This is a small letter of the omega. You normally familiar with the capital letter of omega, Greek letter, right? The small letter is the omega like this. Okay, so if the double bond present at this position, count from the end of the chain, the end of the line at carbon number 3, so we call omega 3. But if the first double bond counting from the tails is present at carbon number 6, we call omega 6. This is how we call the unsaturation and the position of double bond in the polyunsaturation. Okay, so we have this saturated, unsaturated, and polyunsaturated fatty acid. So now we have to look at the physical properties of this, because physical properties is almost always very important for the character of this kind of lipids. Actually, we have to look at both things, physical properties and the chemical properties. So let's look at the physical properties of this fatty acid first. As you know, from the structure, we have non-polar on the right hand and very polar on the left hand side. So if you have maybe 1 mole of fatty acid, they have to pack up together by intermolecular interactions. So for example, this is stearic acid. If I have more than 1 stearic acid molecules, it would be something like this. Right? So they can pack up nicely, but if your fatty acid is unsaturated like this, and as I say, normally unsaturated fatty acid appeared as cis isomer. Because the hydrocarbon chain is curved down here, so if you have 2 molecules, okay, on the left hand you have hydrogen bonding. So this carboxylic acid part come close together using their hydrogen bonding as an intermolecular interaction. So after that, on the right hand. So as you can see, you cannot push the chain to the right because this is curved down. So by the bulkiness of this side chain, your structure of this fatty acid have to curve down because you cannot go straight up to the right hand like this. And if you have more than that, as you can see, the packing of unsaturated fatty acid is very difficult comparing with the saturated fatty acid, which can be packed up together nicely in both sides, in hydrophilic part and the hydrophobic part, right? So as a result, normally we found that the saturated fatty acid has higher boiling point comparing with the unsaturated fatty acid. For example, if you have C16 stearic palmitic acid, saturated fatty acid and unsaturated fatty acid. The saturated fatty acid of C16, melting point of this MP, melting point of the C16 saturated fatty acid is about 60 degrees Celsius, and the unsaturated fatty acid melting point is about 0 degrees Celsius. What does that mean? Does that mean, so it means that the saturated fatty acid C16 appeared in solid phase, but in ambient, the unsaturated C16 is appeared as the liquid phase because the room temperature is higher than the melting point. And if I increase the number of carbon to be 18, so obviously the London force on the right hand side is stronger because you have bigger size of the molecule. So the London force, which is the dispersion of electron, resulted from the dispersion of electron, is stronger. So saturated fatty acid for C16 is about 60 degree melting point, but the C18 is about 70 degree melting point. And if you have cis isomer of this, the melting point of this one is dropped to be 13. This is unsaturation. And if you have like di-unsaturation, cis and cis isomer, so it dropped down a bit more to be -5. This is 1 double bond, and this is for 2 double bond. So as you can see, with the cis isomer, the packing system is going worse. So if you have more double bond, the bulkiness and the steric hindrance effect of the side chain on the right hand side is getting worse and worse. So melting point is decreasing down from 13 to -5, thing like that. So it depends on two major factors: the number of carbon or the size of the hydrocarbon chain on the right hand, and also the number of cis isomer, the number of the unsaturation. So degree of unsaturation will tell you roughly about the physical properties of your fatty acid. Okay? But yeah, fatty acid which contain double bond and single bond, you have another thing that very differ from these two type of fatty acid, because both of the fatty acids you have carboxylic acid, but for saturated you don't have the double bond, but for unsaturated you have the double bond. So we have some kind of reactions to your alkene. No? So if we want to talk about the reactions of the carboxylic acid, it's quite the same. You can condense the carboxylic acid with alcohol, producing all this kind of thing. But if you look at the double bond can also react with something else. So if you start from the double bond like this, one of the things is your double bond can react with like iodine molecules and undergoes halogenation or iodination. So what happens is your double bond undergoes addition reaction and you end up with the diiodol thing. So this is the reaction that we normally use to check up whether your lipids contains double bond or not, or contain how much of the double bond in your mixture using this iodination, because it's very practical to be used roughly by starting from kind of a test tube, put your lipid inside, whether it can be fatty acid solution or it can also be fat, oil, triglyceride, any kind of thing, and then afterward you drop the iodine. Okay, you drop the iodine into the structure, into your solution. So iodine will be eliminated by this reaction. No? So the color of iodine is deep magenta color. So it's bleached down by the double bond, right? So if you still have the double bond in your solution, the iodine color disappeared. But once the double bond, all the double bond was completely destroyed, then you will see pale pink color indicating that all the double bond is already destroyed. So the number of iodine you use can then indicate directly how much of your double bond in the mixture. Okay, that's one of the reactions. Another very important reaction is your double bond can undergo oxidation. The oxidation with oxygen gas in the atmosphere together with the water. The double bond over here was oxidized by this kind of reagent, and after oxidation, firstly, you have kind of this reaction, intermediate. So this is the very first intermediate, happens after oxygen gas take one electron from your double bond and you have this one. This is diradical compound, diradical which is very reactive because as you can see, you have free electron like this. So the radical over here undergoes further oxidation process, and at the very end, you may end up with kind of carboxylic acid. Okay, so it's simply cut down the double bond over here. So this is the final product, the actual final product. But along the way, you may pass some other kind of intermediates. Okay, but what I want to show you here is the diradical over here, which is very reactive, and yeah, it's very toxic as well. It's concerned to be carcinogenic, or the substance that create cancer in the cells, things like that. So if you have the double bond and then you use kind of vegetable oils or any kind of oils containing so many double bond, and you just deep fry things, right? So it happened to create this diradical, right? So it's not very good using high unsaturation fatty oil, thing like that, in order to do cooking in the deep fried or prolonged heating, because it's kind of accelerates the production of the diradical carcinogenic compound. Okay, so that is the kind of thing. So this is two major reactions that I want you to know on the double bond iodination to check whether your fatty acid is saturated or unsaturated, and the oxidation process. Okay. Now, this is roughly the properties of fatty acids. Now, from the properties of fatty acid, especially for the physical property of the fatty acids, you can now describe the properties of other derivatives. So, then, from now, I will give you the kind of structure of some fatty acids, kind of structure of some lipids, and I will give you some assignment. So you know the intermolecular interactions, right? The hydrogen bonding, London force and everything. So after we look at the structure of the fatty acids, and I already described how related about the saturation, unsaturation, and melting point, boiling point, thing like that. You may think about this kind of thing furthermore, and then you may answer my questions in the assignment next. In the discussion part, because you know all about the basic principle of the fatty acids and everything, so now I'm gonna let you use that kind of basic principle, intermolecular interaction and everything, to describe the physical properties of the lipids. Here on your left hand, I have choices from A to F. The A is saturated fatty acid. B is unsaturated fatty acid. To be exact, A is stearic acid. Okay. And B is oleic acid. Then C is the salt of the A, salt of stearic acid. So it's the sodium stearate as a salt between sodium hydroxide reacts with the stearic acid by acid-base reaction. It's very common. And then D here is the phospholipid. As you can see, we have the core of glycerol, and then we have stearic acid for both chain. On the left hand, condensed with the phosphoric acid, you have phosphate ester bond labeled in green here. So this is phospholipid of A. E, this is the phospholipid of B. So the difference is the A, phospholipid of A is unsaturated, and for E, this is unsaturation. Right? There are two unsaturations over here. And then F is the sphingolipids of A, of stearic acid. So this is the choices. I want you to use this kind of molecules to answer these two questions. So you have to think about the physical property and everything. The first question is, when we just dissolve all these things into water, so they can form some kind of arrangement. And at the end, I have actually four choices. The first one, I have individual molecules dissolved in water. In choice 2, they form kind of micelles. You know the micelles from your high school, from your biology, you know? So it's a kind of molecules that pack themselves into spherical structure like this. And then the third possibility is the vesicle. Vesicle is similar to micelle, but instead of using molecules packed themselves into spherical bowl like that, they form the bilayer. You may heard the name lipid bilayer in your in the biology class, right? So from lipid bilayers, as you can see, there are two layers of the molecules. They can curve up and making a spherical bowl, but very huge. And actually there is another possibility, the possibility number 4, which is insoluble in water. Okay, so we have, as I said, 6 choices. So put these 6 choices into 4 categories here. And the last one, this is a nerve cells. So nerve cells, you've learned from your high school biology class that the structure contains 2 kind of parts, dendrite and axon. In dendrite part, this is a rigid core of the cell structure. And then with the axons, this is quite flexible because the axon can flip up, down, and move along the way. So we have rigid core and a flexible tail. What I want you to know or discuss is, can you predict what kind of these 6 substances can be found in rigid core and the flexible tail here? So what is the major component? Just select one of these for the flexible tail and one of these for the rigid core. Just that. Okay? So this is the thing that I want to let you discuss and think about all of this kind of thing. Then I will show you the answer and we'll discuss more in detail in the next clip. Thank you very much.